The universe is a chaos. To comprehend it, humans have assigned numbers to it, and this is the metric system. In this metric system, we have SI units, which is essential for us to comprehend and communicate about things like mass and length. For example, when a child and an adult measure the length of the same rock using their feet, they might have a different measurement of the length since the size of the feet are different. The SI units consist of 7 base units, which are meter, kilogram, second, ampere, Kelvin, mole, and candela. Meter is used for length, kilogram for mass, second for time, ampere for electric current, Kelvin for temperature, mole for number of elementary particles like atoms, and candela for luminous intensity. 4 of them have been redefined, and this redefinition will come into force on 20th May 2019.
Originally, the kilogram is based on a metal cylinder stored underground in Paris. The International Prototype Kilogram, IPK, also known as the Big K. After the redefinition, the Big K will no longer be a kilogram. The new definition relates kilogram to the equivalent mass of a photon's energy given its frequency through Planck's constant. The Planck's constant is used to relate the frequency of a photon to its energy. But what is a photon? A photon is the elementary particle or the smallest thing that makes up light. So what does it mean? From this relationship, a simple way to derive 1 kilogram is as follows. For example, take a photon with frequency of 7.55 times 10 to the power of 32 per second. Its energy is equals to the Planck's constant multiplied by its frequency, which equals to 0.5 joule. This is equivalent to the energy of a wooden block of mass 1 kg moving at a speed of 1 meter per second. Thus, 1 kg is equal to the mass of this wooden block.
For Kelvin, the original definition is based on the triple point of water. The triple point of water is a certain pressure and temperature where ice, liquid water, and vapor exist at the same time. When a beaker of water reaches triple point, you can see freezing and boiling occur simultaneously. The new definition of Kelvin is based on Boltzmann constant. The Boltzmann constant is used to relate the average kinetic energy of particles in a gas with the temperature of the gas. When temperature increases, the average kinetic energy of the particles increases, thus allowing particles to move faster. Based on the Boltzmann constant, when the temperature increases by 1 Kelvin, the average kinetic energy will increase by 1.380649 times 10 to the power of negative 23 joule. So, 1 Kelvin is defined as the temperature increase that will result in an increase of this amount of energy.
Next, the original definition of ampere is defined as follows. Imagine we have 2 very thin, very long wires which are placed side by side and separated by a length of 1 meter in a vacuum. When 1 ampere of current flows across the wires will be attracted by a force of 2 times 10 to the power of negative 7 Newton. This is how 1 ampere was defined. The new definition of ampere will be based on the elementary charge, which is the amount of electric charge Q carried by a single photon or electron. Current across a wire is the amount of electric charge flowing in 1 second. 1 electron carries 1 elementary charge, so 6.2415093 times 10 to the power of 18 of electrons will give us 1 coulomb of electric charge. Thus, the new definition for 1 ampere is the electric current which corresponds to the flow of the charge carried by this amount of electrons in 1 second.
Furthermore, mole also has its definition changed as well. Before the redefinition, 1 mole is defined as the number of atoms contained in 12 grams of carbon-12. In the new definition, 1 mole is now defined based on the Avogadro's constant 6.022140076 times 10 to the power of 23 per mole. As we often use a couple to mean 2, a dozen to mean 12, and a gross to mean 144, chemists now use a mole to mean this number. For example, 1 mole of helium atoms will be defined as containing this amount of helium atoms.
The redefinition is important as the previous definitions have flaws. For example, the old definition of kilogram was the mass of big K, but the mass has been reported to be diverging. This makes a definition that is based on a physical object inconsistent and unreliable. In addition, it is very hard to get access to the big K. The old definition of mole was based on 12 grams of carbon-12. Thus, when kg is redefined, mole has to be redefined as well. Since the old definition of Ampere is dependent on force, and force in turn is dependent on kilogram, scientists have decided to change it as well. Besides, the old definition of Ampere relies on a setup that is difficult to replicate in practice. Apart from this, the old definition of Kelvin is based on the triple point of water, which involves complicated methods for accurate measurement in a laboratory. With the 2019 redefinition, all SI units have been made derivable based on exact numerical values of fundamental physical constants. Changing the definitions of SI units does not make much a difference to the current scale of measurements, but this is the intended results of doing so. The point of this redefinition is to keep the system consistent and reliable before shaking things up. After all, the metric system was intended to be a rational, universal set of units for all people for all time. The words of a French mathematician and philosopher known as Marquis de Condorcet. In an effort to make SI units consistent and reliable forever, the redefinition of SI units indicates a huge leap ahead, as all SI units are now defined based on the way nature is and are no longer bound to physical objects. The kilogram is dead but has been reborn as something much better, the kilogram.